So we now look at some examples related to circular motion that involve centrifuge. So a centrifuge works by spinning super fast. This means that there must be a very large centripetal force that's acting. The object at A would end up traveling along a straight line, except for that inward force that's produced by the end of that test tube, if you will. So that inward force pushes that object sort of inward so that it actually travels away from its straight line path, so being pushed inward. Now, for a typical centrifuge that you might use in a chemistry setting, a typical centrifuge might rotate around at 50,000 RPM. If this 4 centimeter tube is located 6 centimeters from the axis of rotation, we could create accelerations that are about 1 to 2 million times the acceleration due to gravity. Now, since typically a centrifuge is used to help speed up the effect that gravity would have on maybe settling out maybe some sort of the sediments that are part of a chemical reaction, a centrifuge can sort of increase the rate at which that settling will occur, so they can oftentimes be very useful. Now, fighter pilots will train in a centrifuge to withstand up to 7 to 9 G's of acceleration for small amounts of time. Fighter pilot would need to be able to withstand higher accelerations than they're normally experiencing, just in order for them to be able to maneuver around in their jet and not have the high accelerations cause any damage or cause them to black out. Now, in a rotating space station, you oftentimes will see a space station that has occupants living inside of it, and in order for them to rotate, or in order for them rather to simulate gravity, what they do is they rotate the cylinder. Now, they would live in the outside portion of this cylinder, so that would be like their floor, if you will. And then the inside, or the center of that, would be sort of upward. So up is always pointed towards the center. And so this would be the direction of up, no matter where they were. So they would always feel that upward is towards the center. Now we're going to look at an example in which we determine how quickly we would need to rotate that space station in order to simulate gravity here on Earth. And what you will see as we look at this example is that we can really simulate gravity for any planet or star that we might be interested in going to. So a space station might consist of a circular tube that's going to rotate about its center, sort of like a tubular bicycle tire. The circle is formed by the tube, has a diameter of about 1.1 kilometers. What must be the rotational speed, and we'll call that out in revolutions per day, if we're going to have an effect equal to gravity at the surface of the Earth? So the person that would be inside of this thing, or the people, would end up sort of living on the outside of this outside wall of this space station. So this might be the person, and they're walking around back and forth along here. This would be the floor, and this would be the ceiling. Now, our job here is to try to create a situation in where that person is feeling the effects of gravity, if you will, without actually having the Earth or some other object there to sort of pull on them. So what we're going to do is we're going to try to simulate the effect of gravity by having the walls sort of push them inward. Now, I want to draw the FBD for that person right over here. So here we have that person. Remember, up is towards the center. Let's draw the normal force. Now, the normal force would be the force that the wall is sort of pushing inward with. So that force there, which we've been calling N, would be the force that they're feeling from the wall pushing them inward. And remember, we call that N because it's perpendicular to the surface. Now, there is no other force acting on this person. As they rotate around, and I think, let's see, yeah, this thing is rotating sort of counterclockwise. So if it wasn't for that force pushing them inward, they would end up traveling along this line here, because that's the way that they're currently moving. So the wall must sort of push them inward in order for them to be moving around in a circle. Well, that inward force is that normal force. Now, that's the only force that's acting. So if I want to determine the rotational period for that to feel like it would feel here on Earth, we need to then use Newton's second law for circular motion. So let's go ahead and do that. sum of the forces centripetally is equal to m times a sub c centripetally. We see that there's only one force acting in the centripetal direction. So that one force is easily found to be just n. That would be equal to m times, now let's see, a sub c. We had two ways for us to calculate a sub c. One was v squared over r. That would be the tangential speed over r. And the other way that we could find the centripetal acceleration was 4 pi squared r over t squared. Now, because we're looking for the rotational speed, you might think that that means I'm going to look for v. Well, because I'm looking for revolutions per day, that's most easily found by using this version of the equation. So let's go ahead and write a as 4 pi squared r over t squared. And then ultimately we'll try to find t there, the period. Now this next part's a little bit tricky. On Earth, the person just standing there, maybe like that person there, would feel something like this. This would be the forces that are acting on a person on Earth. The Earth would be pulling them with a force called the weight of that person. And let's see, the ground would be pushing them up with a force called N. And that N is no different than this N. So I'm actually using the green color to make sure you realize I want them to feel the exact same force that the ground exerts here as they would here on Earth. So we want that normal force to be equal to their weight on Earth. So let's replace the normal force. I'm going to replace N with what they would feel on Earth. So replace N with the normal force they'd feel on Earth. Okay, so I'm going to replace that value for N with that. Now, that would be equal to their weight, so let's go ahead and replace N with M times G. Okay, so that replacement, do some color coding here to make sure we see that. That is what they would feel on Earth. Now that would be equal to, let's see, M times 4 pi squared r over t squared. We notice right away that the mass of that person will end up reducing out of that equation. So it's the same on both sides, it reduces out. That means that I really don't need to worry about whether or not it's a person, it's a dog that they're bringing along with them to the distant planet, or what have you. The mass will end up reducing out. Now I'm looking for t, so let's go ahead and solve that for t. Let's see, t squared would be equal to 4 pi squared r over g. And let's take the square root now of t, both sides. So t would be equal to the square root of this business. And I can simplify that a little bit further by taking out the square root of 4 pi squared. So that would be 2 pi times the square root of r over g. And that would be the period of that space station's rotational motion. So that would be that period. We can go ahead and compute that for this problem. 2 pi times the square root, the radius would be half of that. So 550 meters. Now I want to simulate gravity for Earth, so let's use g to be 9.8 meters per second squared. I could, in fact, if let's say they were going to Mars, I could make this be more like 3.7 meters per second squared so that they would feel like what they're going to feel on Mars. So I could actually use this as a way of sort of preconditioning the body to be able to respond to whatever kind of gravitational field we're going to eventually be in. Now for this particular problem, we're simulating for here on Earth, so let's go ahead and calculate that. That number turns out to be about 47 seconds. So that period, that would be the time to complete one cycle. So really what I'm asking for is the number of revolutions per day. That can be found by using that value for t. So let's go ahead and write that out. Let's see, t is 47 seconds to complete one revolution, Well, let me change that. Let me take that as 1 over the period. See what that does. That would be 1 revolution for every 47 seconds. Now, this might be a little bit easier to see how we're going to convert that into revolutions per day. So if I take that as 1 revolution for 47 seconds, well, I know that there's 86,400 seconds in 1 day. And so I can just do that as a little conversion factor. Let's take 86,400 and divide that by 47. And what I see is I need to rotate that around about 1,838 revolutions per day. For that particular space station, if I rotated at that particular rate, that person would feel no different than they feel here on Earth. A way to simulate gravity without actually having the Earth pulling on that person.